In this video, I'd like to discuss a very important theorem in mathematics known as the conservative fields theorem. As a matter of fact, we have all the ingredients developed in the course so far to actually prove this in complete detail, and I have done this in my notes. I will not go through every single detail here. I'll just highlight some of the features. So first of all, we are looking at some region in R3, although this can be extended to higher dimensions. I'm just going to stick with R3. The region A is a subset of R3, and we're going to assume that it's simply connected, which means that a curve can be continuously shrunk to a point. An example of a non-simply connected space would be something like a torus. So if I had a bagel, the surface of a bagel, that is contained in R3 because it's there in real life. But this is not a simply connected space, because if I take a curve like this, I cannot shrink it to a point continuously. You cannot go past this hole. Or for example, another curve I can take is the one that goes around the torus like that. That also cannot be shrunk to a point. So the existence of these two classes of curves makes this a bad candidate for this theorem. In fact, you can easily show that this theorem is violated for something like this. But for something like a sphere, when I say sphere, I mean a solid ball or a potato or something like that, you have validity. In this surface, in this region A, we're also going to consider a surface S. Now that surface is supposed to be an open-oriented surface, meaning that if it's open, it means it's got a boundary. So think of it as a Pringles chip. If you have a Pringles chip in a can, that can would be A, and each individual chip in the can would be S, and the crust, the edge of the chip, would be C. And you can make an orientation choice for the C by using the unit normal, outward normal convention. So you imagine that you're going around this curve with your right hand. There are two ways of thinking about the normal convention n hat. One is if you're walking in a trail around a lake, then the lake always appears to your left. We are assuming that you're walking on your feet and not upside down. So if you walk normally, then the lake always appears to your left, and you're walking counterclockwise. So that's one way of doing it. The other way is just to take your right hand and in the move your fingers in the direction of travel, and the thumb will point in the direction of the outward normal vector. So with all that in place, we can actually define the notions of curl and the path integral around a curved closed path C. So the conservative fields theorem says that these statements are equivalent. One leads to the other as a theorem. So the vector field F is said to be curl free if the curl is 0. Well, that in turn implies that if you go around a closed loop, that vector field, let's just call it a force because that's the usual application. So that force does no work. And also, if it's a conservative field, then the work done by that force does not depend on the path taken. That's the third statement. And the fourth statement is, if it's a conservative field, you can actually find a globally defined, globally in that region, a potential function u, such that f is the negative gradient of that potential function. So these are all well understood theorems in physics, and physicists use this without even thinking on a daily basis. Well, what is the rationale behind this theorem? First of all, let's show some easy low-hanging fruit. How are these two related? Why is this the same as that? Well, let's start with Stoke's theorem. Last week you saw that Stoke's theorem is the theorem that says the double integral over a surface S of the curl of F dotted with n, that vector n there, d sigma, is equal to the integral, the oriented integral around the curve C, which is that curve C, which is the boundary of the open surface S of f dot dr. Well, this is the exact content of Stoke's theorem. So if I claim that the vector field is curl free, I'm basically setting this equal to 0, the 0 vector. And so 0 vector dot anything is 0, and that in turn proves that there's 0 work done around closed loops. So I've shown actually that 1 implies 2. Now let's try to show that if 0 work is done around closed loops, then the work does not depend on the path taken. That's also a pretty low-hanging fruit, and it's fun to show. So I'm leaving all the hard stuff for the notes. So let's show this rather easy thing. Let's take this curve C. Let me rewrite it here. That's the curve C. And let's just choose 2 points on it. Let's call this point A and point B. Right now, the curve C initially did not have any special points, but I'm just going to choose 2 points just to make this argument work. Then this curve C can be broken up into 2 curves. The curve from A to B I will call gamma, and the curve from B to A I'll call gamma prime. So just to make you understand, single arrow is a curve, full curve C. Gamma is the path from A to B, and gamma prime is the path from B to A. Now we are ready to show that if 0 work is done around closed loops, then work does not depend on the path taken. How does the proof work here? It works by using the principle of splitting up the integral, the additive property of integrals, in other words. So if I have f dot dr along the curve C, I can split it up into the integral from A to B along gamma f dot dr plus the integral from B to A along gamma prime, the same f dot dr. Well, I'm using 2, so I can set this equal to 0. Well, if that is 0, then I'm left with a statement that integral A to B f dot dr along gamma, I'll just write gamma there, is equal to negative integral from B to A, because if I move this to the other side it becomes a negative sign, f dot dr along gamma prime. Now all I have to do is use the flipping the limits property of the integral, so that becomes positive because the negative sign gets absorbed when you flip the limit, A to B along gamma prime f dot dr. So we have in fact shown that the work done, which is defined as integral from A to B f dot dr, that's the definition of work done. The work done by this force along the path gamma is the same as the work done along the path gamma prime, or in other words, the work done is independent of the path taken. This is very useful in physics because oftentimes the simplest path is the best path to choose to compute the work. And then physicists are fond of showing that you can choose a hellishly difficult path and it gives you the same work. Well, that's not all that great because it comes from this theorem directly. So we have shown now that 2 implies 3. This is the proof that 2 implies 3. Well, the proof that you get a potential energy function concept is a hard proof, and that is left to the notes of VCO 6. Please read the proof details there. What we're going to do is show some reverse implications. Assuming that there's a potential energy, I'm now going to show that the work done is independent of the path. So let me show you that. So I'll write here 4, so 1, 2, and 3 implying 4. I'll leave it for the notes. Please refer to the notes there. It's an intricate proof. It involves choosing a specially constructed path and making this potential happen by actually defining it in stages. Well, what I'll do now is I'll prove that 4 the work done, I'll show that 4 implies that it does not depend on the path taken. I'll show that 4 implies 3. So what I'm going to do is I'll write WF is going to be the integral from I to f, f dot dr, and let me say here any path. So I'm being bold here. I'm predicting that it won't depend on the path taken. Well, that's since I have given f equals negative, I'm given that f equals negative gradient of the potential function. I'm going to get the negative sign outside. I to f. I to f could have been a to b. I'm just using I to f of any path. The gradient of u dot dr. So let me expand this. The gradient of u is del x u. When I say del x, I mean, so just notation here, del x means del by del x, etc., to save space. So it's del x u I hat plus del y u j hat plus del z u k hat. That's the full expansion of the gradient function, this one here. Dot dr, well, the full expansion of that one is dx I hat plus dy j hat plus dz k hat. That's the infinitesimal position vector dr. Okay, now when I take the dot products, I hats and I hats will interact, but I hat and j hat will give you 0. So the only terms I'm going to get here are the integral from I to f along any path, del x. Now I'll write it in full. Del u by del x dx plus del u by del y dy plus del u by del z dz. I wrote it in full because I want to jog your memory from multivariable calculus, and that you should immediately realize, oh, that's just a differential du. So that's integral I to f any path du. Well, the first fundamental theorem of calculus, any kind of calculus, in this case it's just ordinary calculus because it's one-dimensional integral. The integral of a derivative is just a function. So I'm going to get negative u between initial and final. So this shows that it's u initial minus u final because of the minus sign there. It would be u final minus u initial, but because of the minus sign it gets flipped. So it's u initial minus u final. This shows that the path in between is completely irrelevant. So the work done only depends on the potential energy in the beginning minus the potential energy at the end. Whatever crazy path you took in the middle simply doesn't matter. So that's a great proof. Now the last thing I need to show is that if 4 is true, then the field is curl free. Okay, let's show that. So 4 implies 1, and that will finish the long intricate thread of this proof with this part relegated to the notes. So let's show that. I have to show that the curl of f, where f is negative gradient, is going to be 0. So I'm going to get curl of minus the curl of grad of u. Now we don't know what this is, so we have to evaluate it. So let's try to take the ith component. Along the way you'll learn some useful epsilon ijk tricks. The ith component of this is epsilon ijk del j from the first gradient, del k from the second gradient, u. What I'm going to now do with a minus sign is I'm going to change j and k. So what I'll do is I'll write j as k and k as j. So that's going to give me epsilon I kj del k del j. That doesn't change anything. You're not going to get an extra negative sign or anything like that. I'm just forgetting how I learned my alphabet. When I learned my alphabet song, I learned it as kj instead of jk. So it's a simple bad memory. Now what I'm going to do is I'm going to use the ijk clock, and I realize that ikj is minus ijk. So now I'll use the ijk clock and write this as plus epsilon ijk. And this part is still del k del j u. Now there's an important theorem in partial differentiation theory, and this is where the potential function's nature will come in. The potential function has to be C2. So all the hypotheses that you have built into f will go into this. If the potential function is C2, you can avail of what's called Clairaut's theorem. Clairaut's theorem is a very important theorem in multivariable partial derivatives, and it tells us that the order of partial derivatives can be changed. That is, if you have something, you may have encountered this in earlier classes, if you have del 2 u over del x del y, it's the same as del 2 u over del y del x. You usually do things like this without thinking. You can interchange the order. That's the content of Clairaut's theorem. Because I can do that, now what I'll do is I'll write this. I'm going to bring all that calculation out here as epsilon ijk. And now using Clairaut's theorem, I'm going to write del j del k u. I refer you to the line directly above. I have here a minus sign, and I have the same thing with a plus sign. The only quantity that can be equal to the other if the sign is changed is the zero quantity. So in that subtle way, we have shown that the curl is zero. So that completes a proof of the conservative fields theorem.